me? Yes? Okay, first speaker of the night. I gotta get you guys like energetic. Okay, hi, my name is Vaidehi, and just to get a feel of the room, how many of you here do not have a background in computer science? Me too. Okay, that's a pretty good number. Okay, cool. So I have recently kind of started to like learn computer science from scratch. My background is in humanities. I was an English major. And one of the things that I've kind of been amazed by is the fact that you can do one thing so many different ways. There are a lot of different ways to do something. So I think this holds true to the code that we write. I'm sure some of you have looked at pull requests and had some huge question marks going on in your mind about why someone did something the way they did. I think it's also true for the software that we have and JavaScript frameworks, for example. Lots of different ways to solve one similar problem. But one of the things that I have kind of stumbled upon is the fact that in computer science, there are a lot of different ways to solve one problem. And the thing that I want to share with all of you tonight is the fact that you can write numbers in a lot of different ways. The only thing that you have to keep in mind is how many digits you want to use. So in computer science, there's this term that I've noticed get thrown around a lot called hexadecimals. And I didn't really know what hexadecimals were. And I kind of went down this rabbit hole of trying to understand what they are and why on earth you'd ever want to use them. And it turns out they are the most dope things ever. Like 16 is my new favorite number because it is so powerful. And hopefully in like the next 9 minutes, I can convince you all to love the number 16 as much as I do. So numbers. You can write them using a lot of different digits. The way that most of us are probably familiar with writing a number is using 10 digits. This is also known as base 10. Pro tip, if you want to impress someone, you can just tell them that they're using the denary number system, which I didn't know was what we all use to count. That's what we've been using like since elementary school. So base 10, 10 digits possible. And if you wanted to represent something like the number 205, you can have 10 possible digits per every place value. But more than one way to do something. You can also represent this same number using just 2 digits. Some of you might already know where I'm going with this. You can use base 2, also known as the binary number system. If you wanted to represent the number 205 using just 2 digits in binary, it's 11001101. But we're here to talk about 16. So how can you represent the number 205 using 16 digits? Well, you're going to be working with something called base 16, which is also the hexadecimal number system. But 16 digits to represent 205, I don't even know, like where do you begin? Well, I think in order to understand hexadecimals and the base 16 number system, you have to understand what we're talking about when we say base. So when we say base 2 or base 10 or base 16, what we're really referring to is how many digits are possible per place value. So let's start simple. Base 2, 2 possible digits per place value. We can use the number 0 or 1 to represent a single digit. Okay, let's kick it up a notch. Base 10, 10 possible digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Base 16. Okay, we need 16 digits. Well, we have 10. We got to come up with 6 more. We can use letters. In base 16, after the 10th digit, you can actually use letters from the alphabet. That's what you end up using. And you use A, B, C, D, E, and F. So if you wanted to say like, I ate 16 donuts at DonutJS last night, you could say I ate F donuts. And then you just really have to hope that the person you're talking to like knows hexadecimal, because they'd be like, dude, what are you talking about? But anyways, I digress. So how do we represent 205 using hexadecimals? 205 in hex is CD. Really, I promise you. I'm not kidding. I looked it up because I didn't want to be wrong about this. 205 in hexadecimal is CD. So now we know 3 different ways of representing one thing. In base 2, we need 8 digits to represent 205. In base 10, we need 3 digits. And in base 16, we need just 2 digits. If you take a closer look, you'll kind of notice a pattern emerging. The higher the base, the fewer the digits you need to represent something. This is important. We're going to come back to it in a minute. Okay. Cool. Why does that matter? That's interesting. Why should we care? Well, at the end of the day, everything gets compiled down to binary. And the reason that hexadecimals are so powerful is because there's an interesting pattern between how binary and hex can get converted. So here we have the number 205 represented in binary. A single digit is what we refer to as a bit. Bit is actually short for a binary digit, which is a helpful way to remember what it means. 8 bits make a byte. Hopefully you might have heard people referring to bytes. We probably don't think about them as singular things, probably as megabytes or gigabytes, but that's ultimately what they are, 8 binary digits. So if you can represent 1 byte with 8 digits, that's great. But you know what's even better? Representing 1 byte with just 2 digits. Why should you use more digits if you don't need to? So the fewer the digits, the more information you can actually pack into a smaller amount of space. And this ends up being really powerful. It's a great idea. I'm not exactly sure who thought of it, but I think it's awesome. So how many of you here have had to write CSS at some point in your life? Okay, cool. How many of you, if you were like using, if you had to use CSS to represent a color, would use this syntax? Okay, it's a sizable number. How many of you would use the syntax on the right? Okay, it's fewer of you, but that's okay because I'm going to bring all of you guys together. They're the same thing. You have 2 different ways to represent one thing. In this case, both of these syntaxes represent this color red. Okay, so we have this color red that we're going to represent with this hex code. But what's actually going on under the hood of this hex code? Something really cool. Well, with hexadecimals, we know that instead of 8 digits to represent 1 byte, 2 consecutive digits represent 1 byte. So let's look at 2 digits at a time. These first 2 digits represent 1 byte of information. And if we convert this from hex into base 10, 2e in hex is actually just 46 in base 10. 15 in hex is 21 in base 10. And EC in hex is 236 in base 10. Do these numbers look familiar? Hopefully they do, because we just saw them. It turns out that hex codes, when you convert each consecutive pair in a hex code into its base 10 format, will give you the RGB value. And what's interesting about this is the RGB representation of a hex code is actually something that comes from the additive color theory. And we're going to talk about that in a second. But this is 3 bytes of information. But instead of 8 digits plus 8 digits plus 8 digits to represent this, we did it in just 6. So RGB comes from the additive color theory, which basically comes from this color model where you add certain amounts of color in order to form another color. In this case, you're basically saying, I want 236 parts red, 21 parts green, and 46 parts blue. That's a gross oversimplification, but that's probably enough for today. The idea behind this is that you're adding different amounts of color in order to create another color. And if this is really interesting to you, you should go home and Google the theory of trichromatic color vision. I Googled it. Apparently it's dates back to the early 1800s. And it's the same thing that we use when we write hex codes or RGB codes in our CSS today. The interesting thing about this is if you start thinking about how much color you're adding to create another color and convert it into hex code, it explains why we use 6 zeros to represent the color black and 6 Fs to represent the color white. 0 is the lowest digit you can use in hexadecimals, and F is the highest digit. F represents 16. So when we say we want no color, the absence of color, we get the color black, 6 zeros. And when we say we want all the colors, at the highest possible velocity, we have 6 Fs, which gives us the color white. What's really cool about this is that each of these 2 consecutive digits is 1 byte of information. And each byte can hold 16 times 16 possible color values in it. There's 16 times 16 permutations. That's 256 permutations per byte. This is why when you use the RGB model to represent a color, you can only ever use the numbers 0 through 255. If you've ever accidentally typed 256 and gotten a terrible error in your console, that's why, because there's only 256 possible permutations. Now, I don't know how good your math is. Mine is not that good, so I had to pull out my calculator for this. But 256 possible values per 1 byte times 256 times 256. That's over 16 million possible colors in the color spectrum in just 3 bytes of information, which is pretty rad. So, hexes are one example in our CSS, but they're actually everywhere. They're in ASCII encoding. There is an ASCII table. If you look up the extended ASCII table, there are 256 possible different codes. And if you're not familiar with ASCII, it's often used for representing special symbols or translating between languages. It's also used in hex speak. Hex speak is often referred to as magic debug values. So programmers used to put hexadecimal values in their programs, and when something would go wrong and it would break, and this long string of who knows what got spit out, they would look for these unique little hex values. So some of the most common ones are dead code. Dead beef is another one. They're a bit odd. This is from the 80s, so I don't know what was going on then. But hex speak is just hexadecimals. Also, the IPv6 IP addresses also use 8 groups of 4 hexadecimals in order to represent an IP address. Not all IP addresses use this protocol, but if you've ever seen one, you'll actually be able to see that they're grouped by hexadecimals. What's really interesting, I think, about learning about all of these abstractions is that none of us type binary into our computers. At the end of the day, that's what it all gets compiled down into, but we're not typing this. But we use this abstraction. And I think abstractions can be super intimidating. They were for me to learn, until you realize that abstractions are just that. They're abstractions, they are not magic. You can understand and you can unpack what's going on there if you just remember that they were pulled into a little magic black box for you, but that doesn't mean you can't open it up and figure out what's going on. And I think when you start looking at what's going on under the hood and you start understanding abstractions, that's what really makes them magical. So if you're interested in abstractions or computer science, or you just love nerding out about hexadecimals, I'm writing a weekly series on the fundamentals of computer science, which you can find right here. I publish every Monday, and I publish on different topics. So yeah, I hope you'll join me in learning more about all these cool things, including hexadecimals. That's all I have for you. Thank you so much.